connecting again. So, well, we are restarting the recordings. So just to make an introduction, it's on behalf of the Brazilian Logic Society and of the Logic Interest Group of the Brazilian Computer Society, it's a pleasure to have you all here in the Logicians in Quarantine seminar. In a few minutes, Professor Marcelo Finger will begin with his talk, Logic in Numbers. So please wait a few moments. And we would kindly ask everybody to shut your mic and cam off during the talk, just to reduce data flow and avoid problems with a not so good connection.
Hi, I'm back. Sorry for all the trouble. I think I found out what happened to my system. I invented a new way of doing this presentation without crashing the system. I'll try again, and just tell me if you can see the presentation. It's now on here. I don't know where you stopped listening to it, so I'll start from the beginning, okay?
We can see it, Marcelo.
Can see it? Okay. So now I'm presenting it in a different way, as I do in my classes. So this is a well-established way. So I'm talking about logic and numbers. This is a research project or research line that I've been pursuing the last 9 years or so, and basically I'm trying to find a principled way of combining logic and numbers. So basically probabilities and counting with the logic. Um, uh, I'm not sure if that's what's. I'm gonna present it this way. Maybe it'll be better. No, no, this way. So this is the motive. I'll give a motivation. About talk formally about quantitative logic reasoning. I'll give you a joint view, and then I'll conclude. So this talk is not about machine learning. You can see that machine learning needs knowledge representation, but I don't know how to integrate what I do with knowledge representation yet. So I'm not going to talk about that. So the grand plan is to combine some form of logical reasoning. Here is the axiom of induction, which is very complex. When you put it to a system, it becomes undecidable, with some form of mathematical or formula. This is a Schrödinger's equation, which is incredibly hard to solve, but I'm being much more modest than that. So I want to do some things in a principled way. So exactly what I mean, I believe I stopped here or I fell down here. I'll keep on going. Bruno, could you please tell me, go on? I'm listening to you because otherwise.
Yes, we are listening to you. It's perfect.
Okay, good. Thank you. Keep reminding me I'm alive. I need that. So here I have an example of 3 friends that go to the bar every night. The people at the bar, they tell us, hey, these guys come here. At least 2 of them come here every night. But if you ask each of them separately, they will say, oh no, I only come here 60% of the nights. The rest of the time, so this is an example that combines a categorical statement like every night at least 2 of them are at the table. You can express that in logic. At least 2 out of 3 are true. And here I say, if you ask them, do you come here every night? They say, no, I only come here 60% of the nights. So this is the 3 friends that come at the bar. It doesn't sound very serious. So I'm changing. I'm giving a different example. It's a doctor investigating a disease. It's very fashionable these days. And she's examining the roles of 3 genes, G1, G2, and G3. And she formulates a hypothesis. At least two genes have to be present for the disease D to develop. And then she checks the data, and she sees that 60% of the patients have G1 active, 60% of the patients have G2 active, and 60% of the paper has of the patients have G3 active gene. And the question is the hypothesis consistent with the data? So now this looks much more serious way to present this logic and probabilities, logic and number, than the previous one, but it's the same, exactly the same problem. If you formalize them, they are identical. I mean, they are isomorphic. It's the same thing, the two ways of seeing the same problem. Here it's presented as a hypothesis that is a logical hypothesis, and here's a data that's probabilistic that we want to check if the hypothesis is consistent with the data, and it isn't. But anyway, so this is an idea that combining logic with probabilities is a kind of a zombie idea. It was proposed originally by a guy called George Boole in his famous book on the laws of thought. The last two chapters already about combining Boolean algebras with probabilities, and the problem in question is called probabilistic satisfiability, is already present there. So here, there it was a much hard. He didn't have good tools to solve that problem. It was in today's terms, we know that the tools that Boole had, it was double exponential solution for this problem. And then it died because of that complexity. And then it was proposed again in the 20th century by lots of other people studying logic and statistics and good and many other people, until it came to artificial intelligence, and Nielsen proposed this problem again, and it was kind of a polemic because people, oh, you don't read the literature. This is a problem that has been on for quite a while. So it's a problem that it's proposed and dies and proposed and dies, and so we say it's a kind of a zombie idea that refuses to die, keeps walking while that. But we have a different point of view. It's not a zombie idea. It's actually a wildflower that awaits for special conditions to blossom. So here the conditions is to bring together SAT-based techniques and modern optimization techniques, so we can bridge them and put them together seamlessly, and then this kinds of bring us nice solutions to the problem. So now we had to wait for the special conditions to be able to solve all these problems together. So SAT is a very central problem in computer science. It has both theoretical and practical interests. As theoretically, it's kind of it was the first NP-complete problem to be shown, and it's still the most famous and one of the most important open problems in computer science, in theoretical computer science, and has received a lot of attention. And it's also the case that all NP-complete problems can be compiled into it. So if you have a good SAT solver, you can actually solve many other problems. And in fact, we have very efficient SAT solvers that can solve SAT with millions and tens of millions of variables in a decent time, which wasn't believable to be. It wasn't believed to be capable some 30 years ago, when we do that routinely. So SAT has very efficient implementation and has become the assembly language of hard problems. SAT has many applications. Most problem involving deductions passes through SAT. And SAT is logic, of course. Okay, so SAT has this very central position, and probabilistic SAT has not enjoyed such a notoriety until now, but we hope to improve its position in the community. Okay, so now I'm going to change totally to apparently a very different problem. So I will describe here an example that involves people's hobbies. Okay, so we have at most 15 people. Okay, and they have hobbies. Like some are astronomers, some play ball, some sing in a choir, and some dance. Okay, and we know that at least 12 of the astronomers are not dancers, and at least 10 astronomers play ball or sing, and of course all ball players dance. Okay, so we have these 15 people. They have one or more hobbies, and can this is this is the first question, is this uh, statements are these statements consistent, and if they are, can we infer from that? And of course it's very easy to see that at least seven astronomers sing in a choir. It's immediate from these premises that we can tell that at least seven astronomers in a choir. More than that, if it's not the case that at least six astronomers sing in a choir, seven is the minimum number we can do such statement. Well, if you're thinking me crazy for saying that this is trivial, it's not trivial at all. It's an NP complete problem. I mean, it's very hard. I had to play around with the numbers to bring this problem with you. Use my solver. It's totally out of sync with any intuition I have in logic and numbers. But well, but what I think is most striking is that this problem is very similar to the previous one, at least when you try to solve it. We use almost the same machinery to solve. Of course, there are differences. Here, the numbers are integer. There, the numbers were probabilities. They could be any rational or real number, and which makes the other problem easier than this one. Yeah, easier, not harder. So this kind of is a harder problem, but it's the same problem. If you uh, look below the surface, it's the same problem. Okay, and now we have a different setting. It's the same problem with the three friends in a bar, but instead of operating in classical logic, now we operate in some different logic. I'm talking about Lukasiewicz infinitely valued logic. So classically, these guys are a bunch of liars. Why? If at least two of them come to the bar every night, at least one of them must be there 2/3 of the time. Okay, there's no other way. And if they say only 60% of the night, it's impossible to satisfy that in classical logic. But if we allow them to tell partial truth, so if the truth is not complete, but I'm only 50% right, as you can do it in Lukasiewicz infinitely valued logics, then they may be saying the truth. What their statement is actually consistent. There are models for it. So if you change the logic, you convert a bunch of liars into maybe honest people, which is what politicians like to do. But and here, why do we employ Lukasiewicz infinitely valued logic? Because there is a well-founded probability theory for it. Itala can tell you all about this, and there is a notion of coherent Lukasiewicz infinitely valued probabilities in terms of the Definetti Dutch book. So there is a whole of literature telling you about this logic, and this is a kind of very well behaved probability theory on a non-classical logic, on a multi-valued logic. So and again, the same kind of machinery that we use to deal with this logic is the same kind of machinery that we deal with the previous two ones. Although those were in classical logic, here is in a non-classical logic, but it's the same kind of machinery, which I explain to you next. But once you start having partial truth, it's kind of hard to interpret. So suppose these guys they go every night to the bar to watch a football match. So if they watch the whole match, is the truth is one. But if they watch just the first half or just the second half, the truth value of them being at the bar is only 0.5. Okay, so if they watch half of the match, it's not that it's true. It's 0.5 true, and we can deal with this situation by allowing this kind of partial truth. Partial truth is harder to accept in other contexts, like in the context of the doctor talking about the genes. but we may have here that the genes are sometimes active. So in this case, we can introduce partial truth, even though I think it's harder to accept partial truth in this setting. But the problem is still formally still the same. Okay, so now let me formalize. Let me tell you what I understand as quantitative logic reasoning. In For us here, I'm talking about a set of reasoning activities like probabilistic logic reasoning with classical probabilities and classical logic. And I also deal with the reasoning over counting quantifiers. I have counting quantifiers over uh, sentences of first order logic that are only unary. So I have I do not have binary predicates or ternary predicates or anything. All the predicates I'm quantifying on are unary, and this allows us to use it makes the problem uh, only NP complete. Okay, and here we have Lukasiewicz infinitely valued logic, uh, probabilistic reasoning. So we have a probabilistic theory for over this kind of logic, and which is well founded, as I mentioned, and it's also only NP complete. So these are the fragments. They are very well behaved on these fragments in this sense, and we can add many more fragments. I'm studying some at the very moment. I'm studying some some polynomial size fragments of description logics, which is actually first order logic with probabilities, but not counting, and still tractable. Anyway, so there are several logics that we can deal with the same kind of machinery. So why do I put them together? Because they are similar reasoning tasks with quantity. So sometimes we have probability, sometimes we have counting cardinalities. In this case, we have similar methods. All of them are based in linear algebra. And here is a very important point. Okay, people in logic, they don't normally deal with linear algebra. Some of them they don't like, some of them that don't know. But if you're dealing with numbers, you need some machinery to deal with numbers. And linear algebra is, at least in those cases, the right machinery. Some people say, oh, they hide the linear algebra, they cite some theorem that was proven someplace else. Basically, that theorem was proven using techniques of linear algebra, and they use that result. But I don't like that. If you want to effectively deal with logic and numbers, you must be able to attack the numbers in the same way that you have tools for dealing with logic, proving, and models, etc. You must have some machinery to deal with what the numbers do, and linear algebra is our machinery here. And we combine the linear algebra with some decision algorithms, some SAT-based column generation methods. So in column generation is actually the way we combine a linear algebra with SAT, and they all have the same kind of complexity decision. They are only NP complete. So NP is kind of the border between tractable and untractable, and we are there. Okay, and but some of them are more complex than the other. Wait a minute, you just said they are all NP complete, and now you're saying that some are more complex than the other. Yes, and this is not a contradiction, because the class of NP complete problems has internal structure. So SAT is kind of simpler than probabilistic SAT, and probabilistic SAT is kind of simpler than, less complex in fact, than counting quantifiers and Lukasiewicz probabilistic satisfiability. So they are all NP, and some are more when you implement them, and when you have to wait for the answer, some give you the answer quicker than the others. Okay, and well, like SAT, we can solve for tens of millions of variables, while probabilistic SAT we already can deal with 100, maybe 1,000 variables, maybe, not sure, and the others also more limited range that you can still get an answer in a day or in a lifetime. Anyway, so now I'll give you a joint view. I'll present these three problems formally in very similar terms. So I'll give you the screen will be split into three for presenting all these logics. So I have the problems, they look alike. So the probabilistic SAT instance is presented like that. I have a formula phi, and this formula has a probability that's smaller than a number, smaller than or equal, or bigger than or equal to a number, or if the two of them are present, then they are equal. So we can have less than uh, less than or equal, or bigger than or equal to compare the probabilities of formulas and numbers. In CQ SAT, we have the cardinality of sets. So I have the set of all x's such that x satisfy a formula psi1, sorry, where psi1 has only unary predicates, and the cardinality of this set is comparable to a real number, or sorry, a natural number. So the cardinality of set is bigger than C1, the cardinality of some other set is smaller than CK, etc. This is an instance of the CQ SAT problem. And then the LibSAT problem is exactly the same as the PSAT, but the only difference is that instead of calling this the probability P, I call the probability C. I use what Mundici used as a symbol for probability in that context, because C means it's a convex combination of probabilities, so we use the symbol C. Here, the probability here in classical probabilistic logic is also a convex combination. It's not that only here, here is also a convex combination. Here is more than that. So here, just to differentiate, we use the C for probability. So the probability of formula alpha 1 in Lukasiewicz infinitely valued logic is less than, equal or bigger than or equal than some value q1, where q1 is between 0 and 1, just like here. Okay, so the instances, they are very similar. Okay, let's go on in the similarities. We bring all these problems into normal form. So the first step we do is a logician reflex. We put the logics into normal form. So what are these normal forms? In the PSAT instance, we separate the problems into two. There is gamma and psi. Gamma is the set of formulas whose probability is 1. I mean, gamma is the set of formulas that we always want to be true. Okay, and then we have psi, which is the set of formulas that to which we assign probabilities with equals, and furthermore, the xi here are atomic formulas. So we don't have probabilities of a complex formula anymore. Complex formulas are here in gamma, and we only give probability to atomic formulas. And we can transform an initial problem like this into that in linear time, actually, polynomial time, very easy. Same thing for Lukasiewicz infinitely valued logics, the same thing. Gamma is the set of formulas that has probability 1, and the rest has probability assigned to atomic letters only. Oops. And here in the first order logic, we have gamma is the set of formulas that are universal. So for every x, gamma of x are formulas that hold everywhere. And furthermore, we have the cardinalities of sets consisting of atomic predicates only, unary atomic predicates. The cardinality of these sets are equal to values, exactly those values that were present in the original formulation here when we transformed it into normal form. So all these three problems, they start in one formulation. We put them into normal form with things that are true everywhere, and probabilities or cardinalities assigned to atomic sentences. Okay, now next, they all can be presented in terms of linear algebra, but this is a very large linear algebra formulation. So we have a matrix A, which is a matrix of zeros and ones times a probability distribution. This is equal to P. So in order to say that pi here is a probability distribution, um, we must see that all these probabilities add up to 1 and they are bigger than 0. So here we have that this problem is probabilistic satisfiable if and only if there is a linear algebraic formulation of this form. Now, uh, the columns of matrix A, they correspond to valuations. And if we have n variables, we have 2 to the n possible columns. So in principle, this matrix A has 2 to the n columns. And the size of this vector pi here is also exponentially large. So we have a big linear system here that has to be satisfiable if and only if the original problem is satisfiable. Same thing here for the cardinalities. We have a matrix A, which may be exponentially large, times a vector K, which is not now is a large vector. Uh, uh, it's a vector now of integer of actually natural numbers, integer numbers, and we don't need, since this is not a probabilistic, we don't need it to add up to 1, but we need it to be all positive. So it's actually natural numbers. And the matrix A is also consists of only zeros and ones. When we move to Lukasiewicz infinitely divided logic, it's the same formulation as in the classical case, except that A now is consisted of numbers between 0 and 1. A are valuations in Lukasiewicz infinitely divided logic, which are numbers, real numbers or rational numbers between 0 and 1. Okay, so, and in this case, A may even be infinite. Okay, so this is kind of looks nastier than the previous ones. So, but can be reduced to exponential. So in principle, we have solutions for our problems of satisfiability if and only if some very large linear algebraic problem has a solution. So, well, what's the advantage of doing that? Well, the advantage of this formulation is that if there is a solution for if the original formulation is satisfiable, then we have a small solution. They all admit small solutions. So it's a kind of a small model property. If there is a solution, then there is a small solution. In the probabilistic classical and probabilistic Lukasiewicz logic, if they have a solution, if there is a solution, then there is a solution with at most k plus 1 elements of our probability distribution. They are bigger than 0. The rest is all zeros. Same thing here. If there is a solution, there is a solution with at most k plus 1 elements of the probability distribution bigger than 0. The rest is all zeros. So in a sense, we can throw most of the columns of A, we can throw out and just stay with a very small number of these columns. All the other columns are multiplied by 0, can just forget them. Okay. In the integer case, it's a bit more complicated. There is a solution if there is at most this thing here, 5/2 of k log k values that are bigger than 0. All the rest are bigger than 0. But the important thing is that k plus 1, 5/2 of k log k, k plus 1, they are polynomial in k. So if there is a solution, we can guess this solution in polynomial time and polynomial space, which puts all these problems in NP. And as I can encode SAT in all of them, so they are both NP hard and in NP, and these three problems are NP complete. So this small solution property actually puts all these problems in NP. And we can use a technique called column generation to solve them in reasonably efficient ways. Okay. Bruno, are you still there? Am I talking to myself? Am I alive?
Yes, we are listening to you, Marcelo.
Okay, good. Thanks, because otherwise I would be dead. Anyway.
I am here, Marcelo. I am here.
Are you here, Walter? Oh, thank you.
Okay, I'm there.
No,
So
because
please
you
go ahead.
came when I died. I died 3 times before I learned to be
I
alive
see.
for a long period.
I know, but
Uh,
feel free. We tell you if you die.
okay, good. Good to know. Anyway, so well, we can implement them using known techniques, like we have a probabilistic sats over, a CQ sats over. Why CQ? I don't know if I spelled out this is counting quantifiers. This is a CQ over unary predicate. So this is a CQ sats over, and here is Lukasiewicz infinitely valued logic probabilistic satisfiability. We solve these two problems using linear programming, and this problem here using integer linear programming. All of these problems we use column generation. Here to solve column generation, you use a sats over. Here to solve column generation, you also use a sats over integer linear programming. And here we don't use sats over, you use a solver for Lukasiewicz infinitely valued logic, which is kind of more, even though it's also NP complete, it's kind of more complex than SAT. It's there is no linear way of passing from here to here, uh, even though there is a linear way from going from here to here. So it's a kind of more complex, but it's basically the same idea: linear logic with something that generates column using logic. Okay, so sorry, linear algebra with logic to generate columns in those matrices. And we have observed a phase transition for all these logics. This is a property that interests me a lot in practical terms. So there is a conjecture that every NP complete problem has a phase transition, and I've been able to find with the implementations for these logics this phase transition. So this is just a joint view. I'm not going to present you all these theorems. This is just a general overview of why this probabilistic logic, classical or non-classical, and counting quantifiers, they can be seen as the same problem or solved with the same kind of machinery. And I conclude saying that the future, recent and ongoing, we are looking for other logics. We are looking at that tractable probabilistic or description logics, cardinalities for description logics, probabilities and in description logics, probabilistic relational logics. We're all doing that. And actually, the most interesting part here is the representation of rational piecewise linear function approximation of any continuous function. What does that has to do with all that I said? Well, it's all in there. There are techniques that we use for Lukasiewicz infinitely valued logic that allows us to represent any approximate any piecewise linear function, or which are in terms used to approximate any continuous function. So we hope to be able to represent a neural network, which is a continuous function, by approximating it with piecewise linear function, and represent this piecewise linear function with some modification, Lukasiewicz infinitely valued logic. So, so this is ongoing research, and this is basically all I had to tell you now. And if you want, we have freely available implementations. You are most welcome to download and see for yourselves how these things work. And that's my talk. Thank you, and sorry for the trouble at the beginning.
Thank you very much, Marcelo. So now we have time for interaction questions anyway. So please manifestate yourself in the writing chat so we can make a line for the questions.
Where do Bruno?
Well, you are the first one, so you can talk.
Can I?
Yeah.
Okay. So thank you, Marcelo. Very nice. I am a fan of your research, and I like very much this kind of approach. I have a question for you concerning the connection between your way of doing probability and modal logics. right?
Okay.
And the bridge seems to me to be via description logics. Because, you know, description logics are connected to modalities, and your way of making probability or computing probability has to do with description logic. How can I connect then probability and modal logic by means of your way of talking about description logic?
Okay, I'll try to show you that there is some hidden modal logics here. If you see this big matrix A here, which is exponential, and you can throw most of it out, each column of it actually represents, when we put in, why do I put in normal form? When I put it in normal form, each column represents a possible world. Okay, so we have a kind of a representation of all the possible worlds that we can do with n variables. What we don't have, at least not explicitly, is an accessibility relation. So the good part of modal logic models are here. Just they are hidden, or they are encoded into a matrix, and the accessibility relations, I'm not jumping from one world to the other. I'm kind of taking a global view on all the world. So probabilities is a kind of a global, is a summary. So you look at all the worlds and you say, well, I attribute some probability to each of these worlds, and they add up to giving a probability to all the formulas that are true in these worlds. And so the possible world semantics is here, but not the accessibility relation. And in description logics, it's basically the same. But in description logics, it's a kind of model of models. So we have models of description logics, which are modals, which can be done in modal terms. And each of these models, they get a probability, or they get a cardinality. And that's more or less how we do it. So modal logic is here. When we do this description logic, we kind of have to go one level up. I'm not sure if I was clear.
Okay, I see. Even if description logic deals mostly with K, right? The logic K.
Yeah,
the
problem
here
here
simple
with
for modal point of view.
the problem with description logics is that for these things to work properly, each column here is independent from the others. So when you have several models of the same description logic theory, there is no way to guarantee that the models are the same size. So you may have a different number of possible worlds in each model, especially if they are K, and the accessibility relation is different. So for this machinery to work, all the columns have to be independent. So it's very hard actually to say I have the same model. I don't know how to do that. The machinery doesn't allow me, it doesn't have expressivity. If I add this expressivity, the complexity blows up, maybe becomes undecidable, or it becomes the next step. If I add binary relations, it becomes non-deterministic exponential space. Okay, so this is the jump. Okay, and if I add more things, then it becomes undecidable. Okay, so I'm trying to keep the fragments very expressive. To get tractability, the fragments, they have to behave so well that you can see a graph there, or you can impose a graph, and then you get tractability. But it's hard actually to impose tractability on these things.
Okay, nice. Thank you. Thank you.
Mario?
Hi, Marcelo.
Hi, Mario. Thank you. Thank you for being here.
And it's more a remark. And we are talking about, have you come across this modal logic with assignments, with dynamic logic with assignments, that modal logic that you are more worried with assignment, the combination of Boolean values that you can assign to formulas. So the possibles are this combination, and you are not very worried about relations. You are more worried about the assignments.
Yeah,
So
but
that
when you
maybe
do that, do you increase the expressivity of the logic or do you decrease it? I think you increase the expressivity of the logic.
you increase,
And also the
yeah.
complexity.
You have the complex. It's still decidable, but it is exponential. Yes,
Yeah,
that's true.
so if you add here, you probably get this non-deterministic exponentially large
Yes,
models.
yeah, yeah.
Yeah,
That's
you won't have this sorry, the small model, small solutions. You probably lose that.
okay.
Uh,
That's nice. Thank you.
thank you. Uh,
Tem uma pergunta do. Oh, sorry. We have a question from Petrúcio. Is there an easy to explain intuition why the second logic has a such different superior bound?
Here, yes. Well, the underlying linear algebra that we have in these two things is it's basically linear algebra without integers. So basic linear algebra is tractable. So we can solve linear systems in linear algebra in polynomial time. This is a well-known result. While integer linear algebra, where the results of our system, they have to be natural numbers, then this increases the complexity. So the underlying integer linear algebra is already NP complete. Here, just the algebraic part can simulate SAT, where here just the algebraic part cannot simulate SAT. So so making things integer actually makes it harder or more complex in computational terms. And also here we have this result here that you need at most k+1. It's called the Kara-Theodori result, and the Kara-Theodori result for integer systems. This upper bound, it's and at most this number, but it's not fixed. Actually, it's a little bit less than that. The latest result tells me that it's 2.4 something k log k. So I just rounded it to 2.5, and it's not guaranteed that this is minimal, but here it's guaranteed that this is minimal. This is a well-known Kara-Theodori result from the 1920s, so it's a 100-year-old result. And dealing with integers is actually harder than dealing with reals or rationals. Actually, here we can forget we have real numbers. It's just rational. We can do everything with rationals without any problem. Okay.
Any other question or comment? Okay, so thank you very much, Marcelo. I'm going to stop the recording.
Thank you very much. Sorry for all that problem. I don't know why it happened, but we found a solution finally. Thank you for all the patience, and well, I'm here to answer your questions on anything on neural networks or this. Quite available.